Thanks everyone for coming. My name is Kevin Greer. I work at Google in the Waterloo office, just down the street from here. And I lead the team of 5 full-time engineers who work on a product called Foam, which stands for Feature-Oriented Active Modeler. It's open source, so you can go to foamdev.com, see tutorials, documentation, or you can go to github.foamdev.com to see the source. And you can reach me by email, Twitter, or Google+. Okay, so this presentation is actually a Foam program. So everything you're going to see is all Foam, except for a couple thumbnails and icons and one image. Every single pixel is Foam. So Foam is something quite a bit different. Who's familiar with modeling? So only a couple people. So Foam is a modeler. So let's have a look. It's really 2 parts. One is a modeler, and the other is a kind of a library. So it's cross-platform. So on different on different platforms, our library is sort of different sizes, depending on how much of the gap we need to fill in. We generate part of the Chrome browser using Foam, and in that case, we're only a modeler. There's no library. We use the existing Chrome libraries, and we just generate code for that. But in other cases, like JavaScript, where the underlying library is kind of deficient, we are much larger. So a model is basically like a blueprint or a schema, or it's a description. So the idea is what you want to do is give a description or a specification for your application, and then Foam would create it for you. Okay, the things that we let you model are classes, animations, parsers, queries, concurrency, interactive documents. So this presentation is a Foam interactive document, and you'll see a lot of animations in this presentation, and they're all modeled in Foam. Then we have our library, which we do both client and server. On the server, we do Node.js and Java. And on the client, we do Android, the web, and iOS. iOS is handled by a different team at Google, and we can consult them on that. So on the web, we do model view and controller. And in the model, so this is basically our database layer, we do local storage. We can do across the network. We can do offline, an offline sync. And we do query processing and query optimization. One thing, most JavaScript view libraries are actually really only DOM libraries. So they don't let you work with the Canvas or WebGL. Foam has a single unified model so that you can work with any type of these underlying technologies in the same way. We add onto that reactivity, which I'll get into, animation and physics. And for classes, we add a lot of features like packages, traits, dependencies, type checking, and reflection that you would typically get from a transpiler or from some other language, but is missing in JavaScript. So the big thing we often get asked is, well, how does this compare from Angular, say, to Angular, which is also from Google? But Angular is just DOM view library on the web, right? So basically, if you consider the scope of Foam, what something like Angular is doing is a third of a third of a third of a half of a half. So Foam is a much larger scope. And the underlying view library that you use, you can actually, Foam comes with a view library for the web, but you can, it's really agnostic. We've had people use Foam to model applications for Polymer or for other frameworks as well. Okay, so let's have a look at model. One of the most important things we model is classes. So everybody's familiar with classes, like you would have an ECMAScript 6 or Java or C++. Okay, so here's the kind of simplest class you would have in ECMAScript 6. So I'm creating a person and the constructor, and they've got a few properties, first name, last name, age, whether they're married. So this is a class in ECMAScript 6. Okay. This is the model in Foam. Now it looks almost identical. So we call it even class. We give it a name and we list the properties. So these are kind of like almost identical. But if you'll notice, this is data, right? So this is syntax that they had to add to the language in ECMAScript 6, but this is just ECMAScript 5, and this is just JSON data. So I'm saying the name is person, and these are the properties. And then Foam at runtime will go and build you a class from that specification. Well, I say, well, it's kind of neither here nor there, you know, one way or the other. But let's look at some differences. So who's heard of the DRY principle? Okay, so that stands for don't repeat yourself. And that's like a fundamental concept in software development, is that when you do something, you only want to do it once. And there's two reasons for that. One, if you have to do it multiple times, that's more effort. And then also, it leads to poorer quality. Because then if it's in multiple spots, then they can get out of sync. So even in this, we're just looking at a simple class. On the right, I've repeated ID 3 times. So it's here, here, and here. So even just in this, you know, basically 2 lines of code stretched out, I've had to repeat ID 3 times. Whereas in the model, I've only specified it once. Okay. Now here's a Java class, so quite similar. And now it's even worse. So in Java, I have to specify it 4 times because here we've added the types. But otherwise, it looks pretty similar. Okay. So here's actually a fuller Foam model. I've added the package. So JavaScript doesn't have packages, but we add it. I've given types to the properties, so we can type check them. I've even given this here a default value. And now I've added a method and an action. We'll see actions later, but actions are just like methods that are meant to be used in the GUI, so it has extra information so it knows how to use them in a GUI. But otherwise, this looks very much like a class, but it's a model. It's basically a specification of a class, and then we'll build the class from it. But the advantage is we don't need to wait for ECMAScript 6 or ECMAScript 7 or some future version. We get all these capabilities now. So let's go back. So here's Foam. So this animation was written by my 11-year-old son. So I put it in to make him happy. But you can think of Foam as basically a robot. And what it's doing, it's taking your model specification and it's creating the class for you. So here's the code. I'm going to create a person. And I can give it a map of features and it'll create that person for me. So I create the model, it creates the class for me. So far, there's really no advantage except it works with current JavaScript. But normally, in that class, sometimes you might need other methods, like say, for example, hashcode. So if I call the hashcode method on that person, it works. If I change the name and call it again, I get a different value. So normally, that's something, if you wanted, you would have to write that by hand. But Foam has went ahead and said, you might need that, so let's write it for you. But it does it for a lot of other things. Copy from, clone, equals, compare to, even XML support. So any object that's been modeled, you can call to XML, and it'll output it in XML for you. Also, you can do from XML, and it knows how to parse XML. It also can do the same thing to and from JSON. Also, we implement the observer pattern, so you can get property change events on it, which is sort of the equivalent of object observe. Which was modeled after Foam. Now, if I want to bring up a GUI, this is what's called a detail view. So here's the 1 line of code. I just say detail view create. I say the data, that's my person. I say show actions is true. And that brings up a GUI for that person and that action. There it is. Now, if I want to create a material design detail view, I get that version as well. A table view, and this is the 1 line of code I need to create a table view for that. I get a list view. I get a help view if I want to have online help. We have a grid view. We also have a hyperbolically warped grid view, which is pretty fun to play with. We have a query optimizer, a query parser. Then we have databases. If you want to store that data in local storage, IndexedDB, go across the network, have offline sync, store it in a file DAO on the server, MongoDB, Postgres, Google Cloud Store, Firebase. All of those you get for free. So in the same or less work than it took you to write a class, you can create a model, and then Foam will build you all these components. And what this really culminates is in the controller. So we can take a bunch of these parts, like the detail view and the database and the class, put them all together and create a full working app. So here's an example of Gmail written in Foam. And then here we create a UML diagram, and we also create the equivalent of a Java doc from that model as well. And then this is extensible. So anything else that you want to add for your particular platform, you can add those. So now you're programming at a much higher level. You just create your model, and if you want to store it in this database and display it in this way, that's 1 or 2 lines. And so you're just working with views and databases and importing to this format or that format, and that's all 1 line. But there's more. So that's in JavaScript, but we do the same thing for Java. So from that same model, here's the Java code now for the Java class. And so, for example, here's the hash code method, or the compare to, or the append, or the clone. So this is all code that you don't need to write. And talking about not being dry, age is referenced 27 times in this one file. So if I added, say, a new field like middle name, there's 27 spots where I would need to go and add that. Right? And again, from the same model, I can create both the JavaScript and the Java. And so we do that for all these different components. We create them for Java as well. And then we do the same thing on iOS using Dart, or Swift, sorry. So here's the Swift code generated from that same model. And everything that you do, it's a little bit better. It's 23 times spots you'd have to add a middle name, but that's only because the Swift has slightly fewer features. It's not that the language is any better at that. And so we generate all of those as well. And then we could, in the future, add some other platform. Those are the 3 we support right now. Or you could put your stack. So the idea is whatever your stack is, whether it's the ABCD stack, you can create these features. So this is where the name comes from. When we say it's a feature-oriented active modeler, the model is the model. Each of these are features, and then each chunk of features is a platform. So what we're doing is let you write those features in a reusable way, then create your models, and then we kind of multiply them together. Okay, I'm just going to go off on apparently a bit of a tangent for a second. Okay. Anybody know ignore that for a minute. Anybody know what the largest engineering project of the 60s was? In the whole world?
Space mission?
It was the moon mission, was the largest engineering project. Anybody know what the second largest engineering project of the 60s was?
Nuclear bombs?
It was IBM's System 360. So it was such like a huge feat to create a new computer system, a new operating system, that this was the second largest engineering project. And in order to compete with that, they wanted to create a system called Multics. Has anyone heard of Multics? One person. Anyone heard of Unix? Okay, so Unix is basically the basis of most modern operating systems. Android, Chrome OS, iOS, OS X, Linux are all Unix derivatives or actually Unix still. Okay, so this was such a big engineering effort to create a new operating system that it was combined effort between AT&T, which was the largest telecommunication company in the world, General Electric, which was the largest company of any type in the world, and MIT. And so they all got together and they wanted to create this operating system called Multics. And the way they did it, so here, this is a simulation. The little dots represent developers running around writing code. And here on this axis, we have the type of data that you would need for an operating system: users, groups, processes, devices, files, and so on. And across the top, we have the features: sorting, search, paging, printing, editing, etc. And so what they're doing is running around implementing each of these commands and then implementing the features for each of those commands. Okay? But meanwhile, at AT&T, you had 2 guys, Dennis Ritchie and Ken Thompson, the 2 Red developers, who were just kind of using some obsolete hardware in the basement in their spare time, But what they did differently, so they have the same thing, the same data structures and the same features, but they introduced the pipe command. So in Unix, command like ls and ps, it doesn't have those features. Then you pipe it into grep, into sort, into less, or whatever, and then they only had to write those features once. So when we say foam is feature-oriented, well, so is Unix. So basically, two guys, you know, in a kind of a hacker kind of project, they did the software equivalent of putting a man on the moon, right? And how did they do that? Multics, which is dead now, had all of the money, had all the resources, had all the company backing, had all the developers, and yet Unix is the operating system everybody is using today. And what Unix had really going in its advantage, despite all of its disadvantages, was mathematics. But by just coding the perimeter and then getting all these features, it's an exponentially more efficient development paradigm. So here we can see we're graphing. Red is Unix, so at the top we have lines of code. Obviously it's much fewer lines of code because there's only 2 developers. But the utility that they've got is actually increasing exponentially. And they say at this point it's past Multics. And so their efficiency is much higher. Okay. So is that clear how that's working? They're not writing sorting and search and paging for every command. They leave that out, they write it once, and then they combine them. From command line to both GUIs and then the web, we lost that efficiency. And what we're doing with foam is just kind of bringing it back. Okay, so let's look at the foam architecture. It's written in JavaScript, but that doesn't mean that we're a JavaScript framework. Just like if you may have an editor that may be written in C, but that doesn't mean you can only edit C code in that editor, right? So although we're written in JavaScript, we target any platform or any language or any stack. So on top of JavaScript, we add events, then reactivity, then animation, then model view controller, then metaprogramming, and then our integrated modeling environment. But we can generate code for any language. And at the developer, back from the previous slide, you're free to access foam at any layer. So one problem with very high-level frameworks sometimes is that they're great for what they let you do, but anything that they don't let you do, you're out of luck. With foam, you can always go down to the next lower level. So we always are very careful that if there's something we don't make easier, then at least we don't make it any harder. Okay, so this is the full stack conference. So let's talk about how foam is full stack, which we've seen a bit already. So this is sort of how you might typically build an application. So we have the person from the previous slide. We have, in this case, let's say SQL. Then we have a Java backend. We create the database layer, the person class, the part that serves it across the network, some kind of middleware tier. And then on the client in JavaScript, we've got the person to marshal from the network, the person's class or prototype, a bunch of different views, then the HTML and CSS. So this is 15 components in 6 different languages. So we saw that even our single class was not dry because we had to put that ID or middle name in 27 spots. But that was just one of these files. Once you go to all 15, then you've got that property is all kinds of places. But what we do is we get rid of the middleware and we replace it with a foam model, and then we generate all of those components. And then it's up to you if you want to customize them or insert business logic. We have insertion points, but from right off the bat, we give you an end-to-end working system from just your model. But more often than, also we add client-side search and offline data and offline data sync. But here we can also add multiple platforms. So you may not just be the web, you may also have iOS or Android or other platforms as well. And we generate all of these from your model. And how would you do that? Like normally you would have a constant, like the reason if I want to say that the person's first name is 35 characters. In Java or in ECMAScript 6, I can create a constant and say that is the max width of first name is 35 characters, so I don't have to repeat that. But when I'm spanning 6 different languages, where do I put that? But if I put it in the model, and that model spans all of my languages and all my platforms, then I don't have to repeat myself. And then I can be cross-platform full stack and still dry. Okay. Okay, I mentioned it a couple times, but what we do on the data layer is create something called a DAO, which is a data access object. So no matter what database you're going to, we have the same interface. So we create these components for you, and then on the right, you can see this is a query. So I do DAO, I want to skip 200, limit 50, order by timestamp, where, so on and so forth, select, and then group by. So this is actually modeled. This query is data. So just like we take your class, and then we can convert that to JavaScript, Java, Dart, Swift, we can, by doing your query this way rather than in like raw SQL, at runtime we can convert this to either SQL or a Mongo query or just execute it ourselves over something like a JavaScript array. So this is the way you would program against your DAO, and irregardless of whether you're online, offline, you're sync, it's Mongo, it's Postgres, it's MySQL, it's always the same programming model. Here's the interface, so it's kind of what you would expect: put, remove, find, select, remove all, update, listen, where, limit, skip. So it's kind of very simple interface, but that's the only data interface we have. So no matter what type of data on what type of database, it's always the same interface. And here there's a bunch of DAO examples. If you want to look at those, some are quite interesting. Okay, benchmark applications. There's a couple of these. Who's heard of To-Do MVC? Okay, not very many people. So in JavaScript, it's a very popular site where you have this little to-do app written in all the different JavaScript frameworks, and including Foam. So you can go in and have a look and compare the code Foam to all the other ones, and it's much shorter. So I can mark this one off. Done. But there's another one, not so well known, called 7 GUIs. So a guy, for his master's thesis, he analyzed, he was trying to empirically measure GUI libraries. So he came up with these 7 particular GUIs that stressed all of the main things you would need to do in a GUI. And so far, Foam is the only implementation in JavaScript. And so you can have a look at that, and have a look at the code, and compare it to other frameworks. And some are like. Okay. So if you want to learn a little bit more about Foam and get a feel for how the code looks, that's a good place to start. Okay. So the To-Do MVC app that we saw on the previous screen, here it is right here on the right. All of the reference implementations are all written against local storage, which is right here. And so that code, in most other implementations, it's interleaved with the GUI code in those implementations. But local storage it's not very scalable. And so say you wanted to switch it to IndexedDB, which is also in the browser, but can hold a lot more data. Then most of those other implementations, you would pretty much need to rewrite a good portion of the application. In Foam, you don't need to do that. It's a one-line change to say, instead of using local storage DAO, I want to use an IndexedDB DAO, and then all the remaining code stays the same. Or what you can do is IndexedDB, it's scalable, but it's not very fast. We have a caching layer that you can put over top of that, and again, it doesn't change your code. We add the DAO features to the basic array, so you can just use a regular array and everything works. We also work with Chrome storage, Chrome Sync storage. You can go across the network. If you are a Gmail client, we adapt the existing Gmail API into a DAO. We have a generic client and server adapter, so if you want to go to the server and then run MongoDB or a JSON file, we'll do that, Google Cloud Store. And then we have our caching and offline sync, so you can add that to any app. And then we have a bunch of decorators. So often for any particular DAO, what we do is we just, they're kind of like Lego, they all implement the same interface, and then you stack in front of that something to do sequence number assignment or logging or timing or validation or data migration or whatever. So typically you take that underlying basic DAO, add decorators to get up to all the functionality that you want. We have a very sophisticated caching layer. So this is benchmarks done by another team at Google. So they took all the queries out of their application and they compared them to IndexedDB and WebSQL. And here are the results. The blue ones are the foam's caching layer, and it's on average 100 times faster. Now, when you can do something 10% faster or 100% faster, that's great. But when you can do something 100 times faster, then that kind of lets you do qualitatively different things, right? So here's a simple Olympic medal database. So here we can see, I guess you probably can't see it very well, but right here we have 29,216 of 29,216 selected. And I just grab the scroll bar and I can scroll from top to bottom right through 29,000 records. I can sort. If I want to search, I can say first name is Kevin or last name is Greer. And then we see it comes right in. And it also has the counts. So not only, let's clear that. So I pick from. So I don't know if you can see that very clearly, but when I pick the from starting year, every one, it has the count already. So it knows before I pick it how many I'm going to get. And when I pick it, it filters all the other filters. So I'm not getting options that I won't get. So not only do you notice the screen update instantly, like on the next frame, but I have enough time left over that I can also then go ahead and perform every other next query and give you the counts to let you know what those are. And here's say, for example, the color gold tells you how many. I don't even have to click it. As I hover over, it's fast enough that it can update the results just as I swipe over top. Right? And if I want to do, oh, where am I? If I want to run that, so that's 29,000 records stored locally in the browser, and I'm doing all the search offline. But if I want to run that in client-server mode, here I'm going to run a node server. Okay, so I'm going to load this page. And now this is the same one with only a two-line change, and now it's running client-server. So it's a little bit slower because the data is going, but still, you can see. I'm scrolling through 26,000 records. This is going to across the network to myself, and I have all the counts. So if I switch this from a client server to an offline app, I only have to change 2 lines of code, and the performance is still great. Okay. Okay, here's, we added, not only do we have classes, the JavaScript's missing. While we're at it, we add a lot of other features to our classes that you typically don't have, like packages, inheritance, traits is a way to get multiple inheritance without C++'s diamond problem, constants, properties, methods, actions, listeners, templates. And so, if you're waiting for ECMAScript, it's going to be like ECMAScript 15 before you have all of these features. So let's have a look at the code for that. Actually, so that Olympic demo, let's have a look at this. Can you see that? So this is the server. This is the database and the server code. And there's no other classes anywhere else. This is it entirely. We create a Olympics, we create a server. We list our requirements and some imports. We want to create a metal DAO. We say it's an easy DAO. Its model is metal. We want to deduplicate values. That saves memory, assign sequence numbers, and auto index. So if you do a query for something, it'll add the index if it needs on the fly. And then we export that. And so that creates the database and the server, and that's it. And if I change any of those properties, this works right away. And if I want to change my underlying database to MongoDB, I just change this one line where it's DAO type from MDAO to Mongo or to whatever. OK, but what we're going to look now is Pong. So here's the code for Pong. So I create the class for ball, right? And extends circle, so it's just a circle. And then I add some traits physical that gives it mass and velocity. And I add the trait motion blur. So you see the ball has a motion blur. I just add that with that trait. I create the paddle, which is also a circle. And here I extend the trait shadow, so it gives me the shadow. And then here I create the game. But I'll show you something interesting. So if I put a debugger statement in here, I'll load the Pong game. Yep. Oh, syntax error. Wrong spot. And now I look at the code. Like if I use some transpilers, like some of the ECMAScript transpilers or transcript or CoffeeScript or TypeScript, when I go and I want to use that code inside my debugger or inside my profiler or debugger, it's all been mangled. But here we didn't do that. This code is exactly the code I wrote, right? And when I profile it, it profiles the code that I wrote because this is still ECMAScript 5. Now it looks like we've added all these extra features, but we're not transpiling to do it. And notice I didn't have, there was no build step. I just reload and I have the code immediately. So I have all these features that you would get from a transpiler and more, but I don't have the inconvenience of the transpiler messing up all my code or of having to have a build step. Now we have a build step. If you want to make a production app, we will go through and just package up your dependencies and minify it. But you don't need to during regular development. Who knows or is familiar or has used any kind of system for dependency injection? OK, so we also support that. Here's like a little game, Minesweeper. Has 3 classes, game, board, and cell. And in the board, I can extend myself. So I say export as board. And then inside the cells, they need the board. They can import the board. So what this does is you don't have any globals. Foam models are very self-centered. Everything is this. There's no globals. Everything, all the dependencies are managed for you. You just declare what you import and what you export. And all the wiring is handled for you. And then also this makes it very testable because then you can substitute these by just setting those properties on the object with a mock or something else. So again, this is just another example of these kind of advanced language features that we're adding by going with a model instead. OK, one of the big requirements, so we started this project at Google in 2011, and we wanted to edit our models to have both graphical views and textual views. So we were looking for a GUI library that would do that. So really our goal is to be a modeler, not to be a GUI library. But we looked and we couldn't find one. So we modeled one. And so a lot of things that you get for DOM, they take for granted, you're kind of missing when you go to Canvas. And Foam adds them all back. And when you program a view, whether it's a Canvas view or a WebGL view or a DOM view, you code it exactly the same. And so you don't have a different library that you program entirely different. You have one library that does everything. So if I want to do data binding, you have bound the value. And you can see we have a DOM view at the top and a Canvas view, and they both work the same way. Event handling, yeah, that's not a very exciting demo. Configuration, so here's a circle, and I have a property sheet for it. So I can change its size, change its color. Okay. Composition, with DOM, that's easy, you can compose things. But you see here, I've taken two circles, I compose that into an eye. I take two eyes, I compose them into eyes. And I take those along with a bunch of other circles, and I compose those into this kind of creature. Then we have something that DOM doesn't have, which is reactivity. So then those objects can react to other objects in their environment. Then we have animation. So you have normal animation for CSS animation, but that doesn't help you. That doesn't work for Canvas. In Foam, we have a generic animation system, and it works for anything. I can animate DOM, I can animate Canvas, I could animate your salary, right? It's all the same. Any object can be animated. And then we have interpolation. So not only am I animating something from point A to B, but the path I take along the way, I can specify a function for that. So you see these eyes all start and end at the same spot, but they take different routes or different times. You can see. So why is that important? Well, in real-world apps, it's common that you have both text and graphics, right? So if you're saying, I'm only doing text, you're kind of leaving the other half of the world out. So this is, if you've used the Chrome Task Manager, this is a material design version. So I can see all my tasks, but also have graphs. So if I pick any particular item, I can show what percentage of those resources it's using. We have the graphs at the bottom. And also I get a history of its memory use, CPU. CPU may be low now, but maybe it was spiking a minute ago. And this is otherwise the kind of a normal looking Foam app. And we've got the same search, so I could say CPU is greater than 20%, or memory is greater than 500 megs, or it's Gmail. And so often you have this big long list of tasks, and you're trying to find the one that's causing your problem or a particular app, and this one has those capabilities. So anyway, the point is, in real-world apps, that it's typical that you would like to mix graphics and non-graphics. So here we have a spreadsheet written in Foam. And what I'm going to do, and so this works if I change any value. Then all the values update. But if I want to say, I'm going to take time, and I'm going to add that as a cell. Okay, so we're at time 1. But now if I make that a formula and I say equals F0 and 1, now what's it? Sum? It's been a while since I wrote this add. Oh well, I should have looked that up before. But anyway, I can put in time here. Okay, well, I could put in time and I could make it a function of itself and it would animate, and I could animate different values in the spreadsheet. And that's really what we're doing. We have what's called reactive programming in Foam, but that's really just the way a spreadsheet works. So in a spreadsheet, you don't have events and listeners and callbacks and all this nonsense. You just say this cell is that cell plus that cell, or it's the sum of these cells. And the spreadsheet keeps all of that dependency up to date for you. So in Foam, I just say this.dynamic and give it a function. And then anything inside that function is like a spreadsheet, and it just maintains that dependency for me. So here I have a clock, and I say its x is the mouse's clock, and its y is the mouse's y. And then as if I move my mouse around, the clock moves. But then I can also do second order. So I can say that my first clock is a function of the mouse's position, And then my second clock is a function of the first plus some numbers. So if I move that around. Okay. So this is what reactive programming is. It's just that you can declare like a spreadsheet and the system keeps it for you. But now, what happens if we model time? So here we've modeled time just like we modeled the person before, and then it's running. And then I say the clock's position is also a function of time. Well, there's nothing special about time. It's just a regular value. But then you get animation for free. So from this simple reactive programming model, we get this animation, which you've seen in almost all the slides. And we didn't really explicitly have to code it or to do much code. We just modeled time. Okay. Yep. What did I do? Okay, so then we can do all kinds of fancy animations. And what you're seeing here is basically we've got planets orbiting other planets and moons and satellites orbiting those. The eyes are watching one of the planets. I'm graphing the position of something. We've got a clock in the top right. So this is basically just like the spreadsheet, except it's broken out of the cells and it can be graphical. And this is a time wheel, which is tied to the time and it's spinning around. But there's nothing special about time. So if I grab this, I can stop time. So it's not a slave of time, it's a peer. And then I can scratch time like a DJ, and I can make it go back and forth, right? So this is like two-way data binding to time, right? And there's nothing special. It doesn't know the difference between time and the orbit of a planet. Now we can do those formulas, but what happens if any kind of formula we can relate two objects together? What happens if those formulas happen to be from physics? Things like friction, gravity, inertia. Well, then I get a physics engine. But there's actually no physics engine. It's just falls out from this reactive programming. So here I've added gravity to the bigger bubbles, and I've added negative gravity to the small ones to represent buoyancy. And then I let them go, and they're bouncing off of each other. So again, the simple reactivity, we're getting all these extra features from it. Then I can also do collisions, springs and collisions. And I'm not really sure with this one demos, but it's fun. Okay. But in foam, we modeled our code, right? Our models, we said, were just data. And actually, that's why one of the reasons foam is so small. We modeled our model. So earlier on, where you take that one model and then it expands out to these like 50 components, we do the same thing with foam. Foam is basically bootstraps itself. So this is why it's so small. On the outside, it looks like this big giant framework, but it's actually very tiny because it's compiling itself. And the same kind of efficiency gain that you get for your application, we get for our framework itself. Which is then also great if you want to download it over the web, because we don't ship the code, we just ship the model, and then we expand it on the client side, which is why we can see like foam apps load 10 times faster than equivalent apps written in other frameworks, because we're shipping much less. Okay, so we have reactive programming, and our code is itself modeled. So here's this dragon, and I brought up the method for it. So this is the wing method, right? But I can react to my code. Just as I'm a function of time, I'm also a function of the code that defines me. All right, so I can take this. This is the wing code. Let's say rotate a little more. So look, I've got the syntax error right on the keystroke. 20 times, okay, then it's fixed. Then let's make the wings a little bit longer. Oops. What did I do? Oh. Make those a bit longer. But you can see I can just like change the code on the fly. If I had a transpiler, you know, that you wouldn't be able to do that. So it's kind of neat. Let's slow that down. So here's our time. We've got a time warp. Slow it down a little bit more. Okay, so you can just kind of live code this. And so like there are systems to do live coding, but we didn't really have to write one. Because we modeled our data and we have this reactive programming, we can just apply it to our code and we get this sort of thing for free. Well, if you're going to clap, you should do it now because it's not going to get any better than this. Thanks. So in Chrome OS, the system calculator is written in Foam. So we can bring it up here. It looks like the Android one. Except the Android one has one slide panel and we've got two. And we did this as a joke. Somebody said, well, Foam is good for these apps with lots of data. And so we took one app, which we thought, well, what would be the worst case for Foam? Well, something like a calculator. It's just a GUI, it has no data, there's no databases. And so we did that as a demo, and the PM for Chrome OS said, okay, ship it. So we did. And now it's used by millions and millions of users, which is ironic because it was purposely designed to be the worst thing you could do in Foam. Although it is 6 times smaller than the Android version. Okay, so we showed before, we had, so that is shipped, it's fully internationalized, it's full accessibility. Everything you would need to ship that up. And the previous calculator had 4 functions, and this one has 29. And despite that, it's half the size of the previous one. And most of it is going for the internationalization text for 47 languages. Okay, so the reusable controllers. If you look at something like, and this is, I think, one of the most important slides. If you look at something like Outlook and iTunes, one is for email and one is for or for music. But they're almost the exact same app, right? You've got some kind of categories on the left, search on the top, some kind of list of the objects, and then when you pick one, you get an individual one, and then you have some buttons like to either play the song or to send or reply the email. Those are almost the exact same app, just with different data. So in Foam, we actually give you a generic app, which we just call the reusable controller. So here's an issue tracker, right? Here's a Gmail client, and here's a to-do list app. And we have plenty of others as well. And we just give you that for free, and then you can customize it, right? So once we've parameterized that with the model, you can just plug in your underlying DAO. You can customize the citation view or the detail view, and you get that GUI for free with search and sort and everything else. There's a couple Foam tutorials that you can go through and help build a kind of system. So this is this PhoneCat one, and another one is how to build that to-do list app in the previous screen. We ran a tutorial last week in Toronto we walked a bunch of people through that, and some guy called me to his desk and goes, something's wrong. And I'm looking at his laptop, and I said, well, what is it? The app is running, it seems fine. He goes, but I didn't write any code yet. And I said, well, that's what I told you, you know. So there's always like a case where I give this presentation, but I don't think anybody believes me. And then a point when they actually try it and it really works, then they have kind of an epiphany like, geez, he wasn't lying. So, okay, I'll skip that. So because foam, your models are just regular data, then all this sort of toolability, like API browsers, code generators, type checking, linting, all becomes much easier because you're just working with regular data. Okay? And so I grabbed a UML diagram, and just by coincidence, I just picked out of the list one that looked good. And it turns out that it is the UML diagram for the UML diagram drawer. So that's very meta. Okay, so why are we doing this? I don't know if you know, Google's mission statement is to organize the world's information, make it universally accessible and useful. Well, we take a diagram, that sounds like an operating system. So we take that same diagram we had before for Unix, and we graph it out. So we have the features, all the types of data coming down here. We have the features going across the top, and we have the different platforms. And these are all the Googlers coming in, writing all of that code. But what they're really doing is following the Multics model. They're writing each feature for each piece of data on each platform, right? And what we'd like for them to do is follow the Unix model and then move to the edges. Just code the perimeter, not the area, and that would be exponentially more efficient. And so this is what we're doing with foam. Okay. Last slide. So efficiency is really foam's value proposition. So see, we've got like nice little mnemonic. We have a foamy efficiency, so you'll remember that foam is efficient. And we're talking about application performance, application size, and developer productivity, or as we like to say, fast apps fast. Now, I was thinking every slide is a foam program. What would be a good way to demonstrate this one? Then it occurred to me I didn't actually need to write a special slide for this. I could just run all the 25 previous slides at once. So you can see the modifications we made to the Dragon. They're still running, and as is everything else. So right now, I have 50,000 objects, 20,000 data bindings, 7,000 objects are still being animated. And you can go and interact with them, and they all work. So I couldn't have done this in another framework for a couple reasons. I just wouldn't have had enough time. Like, there's 25 slides, but a lot of these have multiple programs. There's actually 50 programs running right now, 40 of which I wrote by myself, one was written by my son, and the other 9 or so were written or co-written by my teammates. So I just could not have, written this many things if foam wasn't productive. And then, if foam wasn't efficient, I couldn't run them, right? So that's kind of proof right there. So you can see, if I move over here, it's still working. Okay, thank you very much.